Hey guys, so it's that time of year. It's time for final exam prep. We have covered all of the new material that we are going to cover in this class, pretty much the entirety of chapters 1 through 5. So that's a lot of material you need to study for your final exam. That is a whole lot of material. You should use the midterm review, final exam review that we're currently working on. You should use your homeworks, lecture notes, any resource you have at your disposal. So, the way these lectures are going to work is I have typed up a review sheet for you that at the point you are watching this, you should have received it from me. Now, what these videos are going to consist of is me going through and I am going to work out all the problems in the review. I find this might be helpful because not only do you get to see how I answer the solutions, you can see how I think while I answer these solutions. My trains of thought, what kind of conclusions do I come to? How do I approach given problems? So I hope that this lecture series on this review will be very beneficial to you. Now, first video up, we're going to kind of start at a random point. We're going to start at limits. Now, it might seem kind of random to you about why I'm starting with limits, but you could think of it as that's where we started in this class. All right? So the bulk of the limits that you might see on your final exam will consist of techniques involving L'Hopital's rule from section 4.5. Now, if you do not know what L'Hopital's rule is, I strongly suggest you go read those lecture notes or watch that video going over L'Hopital's rule. So, here's how we're going to do this. I'm just going to write down problems in this video on limits, and we're just going to solve 6-7 limit problems. And then the next video I do will consist of, I think, related rates problems, and then graphing problems, and then optimization problems. And then next week I hope to hit integration and differentiation. All right? So that's enough rambling. Let's just go ahead and rock out these problems, shall we? So this part is going to be over limits. Let's go ahead and get that nice underline because I like underlining things. All right? Now, I know this might look different than how they usually do. It's because I did not feel like typing up slides and the review and then writing on the slides when I post the review. That just seems like a giant headache. So this is how we're going to do this. It's actually a really neat app on my tablet that I can write things down on. But I'm guessing you didn't click on this video to just listen to me ramble and explain how I'm doing this. So let's get to it. Part 1. Let's do the first one. We're going to call this A. Evaluate the limit. You know what? Let's do it in a different color. Let's write down the problems in a different color. Why? Because I like using different colors, and I can use different colors because, well, it's just a button. Evaluate the limit as x approaches 0 of the square root of x plus 4 minus 2 divided by x. Now, when you're solving these limit problems, the first thing you should always do is plug it in. Now, what happens when you plug in? Well, plug in a 0 for x, that's the square root of 4, which is just 2. So that's 2 minus 2 in the numerator, so that's going to be equal to 0. But when you plug in 0 in the denominator, that's also going to be equal to a 0. So this is equal to a 0 over 0 situation. What happens when we have 0 over 0 situation? Well, there's a couple things we can do. First off, just in case you're curious, 0 over 0 means indeterminate form. When we say something's an indeterminate form, we mean it's a 0 over 0 situation or infinity over infinity situation. Now, if you think back to all the theory we developed in Chapter 2 with limits, we developed a couple different techniques of how to handle situations like this. This would be a situation that would call for rationalization. However, I am not going to do rationalization, as I just pointed out, the numerator is equal to 0 and the denominator is equal to 0, so we can use L'Hopital's rule. So how do we write that out? Since the limit as x goes to 0 of the square root of x plus 4 minus 2 is equal to 0, and the limit as x approaches 0 of x is equal to 0, then by L'Hopital's, which I don't feel like spelling out, we get that the limit as x approaches 0, the square root of x plus 4 minus 2 over x is equal to the limit as x approaches 0 of the derivative with respect to x of the numerator divided by the derivative with respect to x of the denominator. So remember the L'Hopital's rule? It says that if the limit of the numerator is equal to the limit of the denominator of the function, and they're both equal to 0 or plus or minus infinity, then that limit is equal to the ratio of the derivatives of the functions. It's a very powerful tool that we love to use. So that's equal to the limit as x approaches 0 of, now what's the derivative of the square root of x plus 4? Well, that's 1/2 times x plus 4 to the negative 1/2 divided by, what's the derivative of x? Well, that's just 1. Now, that's really messy, so let's simplify this. This is equal to 1, or is equal to the limit as x approaches 0 of 1 divided by 2 times the square root of x plus 4. Alright? And then this is going to be equal to 1 over 2 times square root of 0 plus 4. Why? Well, in this case at 0, this function is continuous. The square root function is continuous at 0. So I can pass 0 into the square root function. So all we have to do there is plug in. So that's equal to 1 over 2 times the square root of 4. And that is just going to be equal to 1 over 2 times 2, or just 1/4. And then that is our answer. So that's enough for that example. So now let's go on and look at another example. So let's suppose now we want to evaluate the limit as x goes to 0 of 1 minus x to the 2 over x. Now, what happens if we just quote-unquote plug in here? Well, that's 1 raised to the 2 divided by 0. And we kind of call the 2 divided by 0, we kind of call that infinity because it's going to get astronomically big. So this is what we would call a quote-unquote 1 to infinity situation. Now, I would like to point out here that this is not actually equal to 1 to the infinity. Infinity is not a number. We cannot raise something to the infinity. Doesn't make sense in this context. So, when it's a 1 to infinity, that's not the situation we normally have for L'Hopital's, right? L'Hopital's has to be 0 over 0, or infinity over infinity. But in this case, we have 1 to the infinity. So how are we going to handle that? Well, when you're dealing with situations like this, a pretty standard technique is to use the natural log. How are we going to do that? Well, let's see. This is our problem, right? But what if we did an alternative problem? What if we solved the natural log of the limit as x goes to 0 of 1 minus x to the 2 over x? Now you could be asking, why on earth do we want to use the natural log? Well, there's about 3 reasons why we want to use the natural log here, besides the fact that it's awesome and it's the natural log. It has very nice properties that we want to use in this situation. So, take the natural log of the limit as x goes to 0 of 1 minus x to 2 over x. Well, since the natural log is going to be continuous at all the points around here, this is actually equal to the limit as x goes to 0 of the natural log of 1 minus x to the 2 over x. Very nice properties of the natural log. We love its continuity on the positive numbers. And also, I like to point out, this is one of the nice things about continuity in general. We like to be able to pass limits through inside and outside of functions to do our calculations. So we have the limit as x goes to 0 of the natural log of 1 minus x to the 2 over x. And now here's the big reason we love using the natural log. This natural log has an interesting property. Where if you're taking the natural log of something raised to another power, we can pull the exponent down. So this becomes the limit as x goes to 0 of 2 over x times the natural log of 1 minus x, which is just equal to 2, because I like pulling my limits out in front, the limit as x goes to 0 of the natural log of 1 minus x over x. So all we did was we changed the problem. We're calculating the natural log alternative to our problem, pass the natural log inside the limit, and use the natural log to pull down this exponent out in front, and then we pull the constant out in front. Now, why did we do this? We did this because the limit as x goes to 0 of the natural log of 1 minus x is equal to the natural log of 1. But what is the natural log of 1? Well, that's just equal to 0. And the limit as x goes to 0 of x is also equal to 0. So now this alternative problem, when we took the natural log and evaluate the limit, now we have a 0 over 0 situation. So we can now use L'Hopital's rule. All right? So this is equal to 2 times the derivative of the top, which is equal to 1 over 1 minus x times negative 1. Why times negative 1? Well, because the inside function here is 1 minus x, and the derivative of the inside is just negative 1. Straight chain rule, divided by 1. Right? Alrighty. So now this is going to be equal to negative 2 times 1 over 1 minus x. Now I made a pretty big problem here. Anyone notice what I've done? Take a second to see if you can notice the mistake I have made. Notice I stopped carrying my limit notation right here. That's a big mistake. Actually, if I was grading written work on this, that's minus a few points there. You cannot forget your limit notation. You have to carry your limit notation with you until you evaluate the actual limit. That's like dropping the plus sign before you add anything. Doesn't make any sense. Now, from here, what happens when we plug in? Well, that's just equal to negative 2 divided by 1 minus 0, which is just negative 2. Now, this is not our answer. This is not our answer. Negative 2 is not equal to the limit as x goes to 0 of 1 minus x to 2 over x. Negative 2 is equal to the natural log of our problem. So the natural log of the limit as x goes to 0 of 1 minus x to the 2 over x is equal to negative 2. And now for the third and final reason we like using the natural log here, we know its inverse function. Slap both sides up into the exponent of e. Remember, the natural log function is the inverse to the exponential function e to the x. So if we want to undo the natural log, raise everything to the power e. Or raise everything by the power e. So this will kind of cancel out the e in the natural log. So that tells us the limit as x goes to 0 of 1 minus x to the 2 over x is equal e to the negative 2. But what is e to the negative 2? 1 over e squared. And so that's how we tackle a problem like this. We recognize 1 to infinity is not a situation that we can use L'Hopital's, but we can do is take the limit of the function, get it into a situation where we can use L'Hopital's, then take this new answer and then apply it to the original problem by simply raising it into the power of e, using the exponential function to undo the natural log. All right, it's a pretty standard technique when we tackle problems like this. So that's it for that problem. Move on to another problem. Let's go ahead, section that one off. Well, you know what? We're basically at the end of the page, so we might as well just go on to the next page. Electronic form, not wasting paper. All right, now let's try another problem. To evaluate the limit, man, that's really hard to do when you're just trying to draw in straight lines. Let's do the limit as x goes to 0 of 2x squared plus x minus 3 divided by x plus 1. Now, before you start doing any fancy techniques, before you start trying to manipulate things, take some derivatives, take some natural logs, stop. You're doing a limit problem. Don't jump straight into one of our many techniques. That's a quick way down a rabbit hole. First thing you should do, plug it in and see what happens. So let's see what happens when we plug it in. So you go to 2 times 0 squared plus 0 minus 3 over 0 plus 1, which is equal to 0 plus 0 minus 3 over 1, which is equal to negative 3. Oh wait, well, that was it. See, on this one, if you start doing L'Hopital's rule and stuff, yeah, things are going to start getting ugly. In fact, if you do the L'Hopital's rule here, you're actually going to get the wrong answer. Yeah, so L'Hopital's is not a magic wand you can always wave. You cannot always do L'Hopital's and just get the straight answer. It's not like a shortcut in these situations. It only applies to the situation it does. You cannot just use L'Hopital's willy-nilly. You have to be careful when you use it. So, in this problem, just plugged it in. We got a number. There we go. That is the limit of this function. So that's it for that straightforward problem. Now let's try another one. Let's evaluate the limit. X goes to 0 of sine of 3x squared divided by x. Let's try this one. Now what happens if you plug in 0? Well, then you get sine of 0 squared, which is just 0 squared, which is just 0, and you get 0 in the denominator. So that's equal to, quote-unquote, 0 over 0, or indeterminate form. So, since the limit x goes to 0 of sine of 3x squared is equal to 0, which is actually equal to the limit as x goes to 0 of x, by L'Hopital's, the limit x goes to 0 of sine 3x squared over x is equal to the limit x goes to 0 of the derivative of the top divided by the derivative of the bottom. Now I'd like to point out again, I'm not doing the quotient rule here. Yeah, this kind of goes against our intuition at this point with derivatives. You know, the derivative of the quotient is not the quotient of derivatives. That is not true. But with L'Hopital's, we're not doing the quotient rule. We're only taking the derivative of the numerator and dividing it by the derivative of the denominator. That's all we're doing. So this is equal to the limit x goes to 0 of, now what's the derivative of sine of 3x squared? Well, this one we got to do a couple chain rules. So it's equal to 2 times sine of 3x times the derivative of the inside, so cosine of 3x times 3. If you have any questions on how to calculate the derivative, shoot me an email. I'll be happy to explain that in more detail. But that's that one. Divided by 1. Alright? So from here, this is equal to the limit x goes to 0 of 6 sine of 3x cosine of 3x over 1. Now here, this is just straight continuous everywhere. It exists everywhere, it's continuous everywhere, it's differentiable everywhere, it's beautiful. Yay, we love it. So we can actually just plug in 0 here. It's equal to 6 times sine of 0 times cosine of 0. Now, what is sine of 0 equal to? That's just equal to 0. And what happens when you have a bunch of things times 0? Well, it doesn't matter what the other things are. This is equal to 0. So how do we do this? Well, we recognize the limit of the numerator is equal to the limit of the denominator, and they're both equal to 0. So we use L'Hopital's rule, and we just concluded that the limit of this function is equal to the limit of the ratio of the derivatives. We calculated the derivatives, and now we were in a situation where we can just plug in the limit. So we did that, and then we got that our overall limit is actually just equal to 0. All right, that's it for that example. Now let's see another one. Suppose we want to evaluate the limit. Good God, I do that every time. Evaluate the limit. X goes to infinity of 3x squared plus 2x over 2x plus the natural log of x. Now, we are taking an infinite limit of this rational function. And since we're taking the limit as x goes to infinity of this function, another way of thinking about it is, we're asking, does this function have a horizontal asymptote? That's another way of thinking about what we're asking here. All right? Now, when you're doing this problem, there's a couple different ways you can do this, and they are both equivalent. They are equal. There is no wrong way in this case which one of these to do. There's some situations where one technique is better than the other. But in this situation, there's a couple equal techniques. The first one is we can use the tower of power that we went over in section 4.4 when we were talking about limits and asymptotes, basically evaluating limits to infinity. So we can use that theory. But also, if you notice, if you quote-unquote plug infinity into this function, can't actually plug it in. Infinity is not a number. Cannot emphasize that enough. So when we quote-unquote plug it in, we get a quote-unquote infinity over infinity. And since we have infinity over infinity, we can actually implement L'Hopital's rule instead. So we can use both techniques. But since L'Hopital's is the one we went over more recently, I'm going to use that technique so you guys have another example of L'Hopital's. So we get that since the limit as x goes to infinity of 3x squared plus 2x is equal to infinity. And when we say a limit's equal to infinity, we're saying it doesn't converge to a real number and it takes off an unbounded magnitude, is equal to the limit as x goes to infinity of 2x plus the natural log of x by L'Hopital's. This limit right here is equal to the limit x goes to infinity of the derivative of the top divided by the derivative of the bottom. Now, what are those derivatives? Well, that's just equal to the limit as x goes to infinity of 6x plus 2 divided by 2 plus 1 over x. Now, let's analyze this denominator, shall we? When we take this limit as x goes to infinity of the denominator, that's 2 plus 1 over x, where x is tending towards infinity. So that 2 is fixed. Doesn't matter how big x is getting. 2 is staying there. It's not going anywhere. So we get 2 plus, now what happens is we take x unboundedly big, arbitrarily big in 1 over x. Well, that means the denominator is going to get arbitrarily big, so the whole thing is going to get arbitrarily small. When something gets arbitrarily small, we say it's equivalent to 0. Excellent. So now this is equal to the limit as x is infinity of 6x plus 2 divided by 2. All right? Because I wrote it out in this funny way is to illustrate this point. So the denominator is fixed at 2. Doesn't matter what happens to x in this case. It's going to be stuck at 2. It's going to stay there. But the numerator, that's going to get unboundedly big. As we punch in bigger and bigger numbers into this 6x term, that term is going to blow up towards infinity. It's going to get astronomically big. And what happens when we say a number gets astronomically big, especially in the numerator? The whole thing gets astronomically big. And when it gets astronomically big, we call it equal to infinity. So this limit is actually equal to infinity. And if you use the tower of power, recognize that x squared is the dominating power, divide every term by x squared, then taking the limit, you should conclude the exact same answer. All right? So, does anybody have any questions about that? Wow, I just heard myself say that to an empty apartment. I've really got to get better at that. I need quarantine in. I usually don't require human interaction, but I've spoken to like 3 people like in person in the past like month, so I'm going a tiny bit nuts. But thankfully I have the math. Man, I turned into that guy. Okay, so moving past that awkward moment. let's evaluate another example. So let's suppose we want to take the limit as x goes to infinity of x to the 1 over x. That's a lot of x's. I laugh every time I say that. I shouldn't, but I do. I can't help myself. Watch along. Yeah. So, I'm going to take this limit as x goes to infinity of x to the 1 over x. So, kind of a way of describing this problem, if you could quote plug in infinity, this is kind of a infinity to the 0 situation. What happens when you raise something unboundedly big to something unboundedly small? Yeah, this is the math version of what happens when an immovable object meets an unstoppable force. Here, the immovable object is 0. 0 is pretty dominant. 0 doesn't move. You multiply it by any number you want. 0 is staying there. It is not moving. 0 is unstoppable. It is an immovable object. Infinity, on the other hand, is an unstoppable force. That thing is taken off towards infinity. Man, this is what I miss teaching in a classroom. I've been doing hand motions this entire time. Anyways, infinity is taking off towards infinity. It is not being stopped. You cannot stop it. It's going towards infinity. But 0 is not moving. It's 0. It's fixed. It dominates multiplication and exponentiation. It dominates it. So, we're doing this problem. We're trying to figure out who wins in a battle between an unstoppable force and an immovable object. You know how we're going to figure that out? The natural log. So, we're letting nature determine unstoppable forces and immovable objects. Let's see what happens. Once again, since this isn't a L'Hopital situation, we have to get this into a L'Hopital situation. Now, how are we going to do that, you wonder? Well, here's how we're going to do it. We're going to use the natural log. We're going to take this auxiliary equation and calculate the limit as the x goes to infinity of x to the 1 over x, which is just equal to the limit as x goes to infinity of the natural log of x to the 1 over x. And now we're going to use the property of the natural log in that little exponent right there. We're actually going to pull it down. So this is equal to the limit as x goes to infinity of 1 over x times the natural log of x. All right. Now, just to simplify this, this is equal to the limit as x goes to infinity of the natural log. I combine that L and N together. Wow. Natural log of x over x. Now here, what happens if we evaluate as x goes towards infinity? What happens? Well, that natural log of x is going to take off to infinity. It's going to be pretty slow, but it's going to get there. And x is also going towards infinity, but much faster than the natural log of x. So there's two things we can do here. We can use L'Hopital's, or we can use the Tower of Power. And to just keep with the trend of what I've been doing, I'm going to use L'Hopital's again. But remember, Tower of Power, another equal way to do this problem. So this is equal to the limit x goes to infinity of 1 over x divided by 1 by L'Hopital's. Now this is equal to the limit x goes to infinity of 1 over x. And so when we evaluate this limit as x goes to infinity, in this fraction, the numerator is fixed, but the denominator is going to get astronomically big. And when the denominator gets astronomically big, the whole thing gets astronomically small, or arbitrarily small. When that happens, we say it's equal to 0. Now, our instinct would be to circle this, go, yay, we got our answer, and move on. But that's not quite the case. 0 is not the answer to our question. 0 is actually equal to the limit, the natural log. The limit as x goes to infinity of x to the 1 over x. That's not our problem. That's the natural log of our problem. But that tells us that the limit x goes to infinity of x to the 1 over x is equal e to the 0. But what is e to the 0? That's just equal to 1. So rather than tackle our original problem, we sidestep it took the natural log of it, messed around with that situation here, and then we get the limit as x goes to infinity, the natural log of x over x. Now we can use L'Hopital, since that's a quote-unquote infinity over infinity. Take the derivative of the numerator, derivative of the denominator, get 1 over x divided by 1. So we get the limit as x goes to infinity of 1 over x, which is just equal to 0. But that's equal to our auxiliary problem, the natural log problem. And so we have to undo the natural log. We use the exponential function to undo it. So we take the exponential function of both sides. And so we get our limit is equal to e to the 0, which is equal to 1. So, so when an unstoppable force goes up to an immovable object, who won? 1. All right. That's all the examples I have right here on limits. Now, if you wish to see more examples, if you look at the section 4.5 notes, there's quite a few examples on using L'Hopitals. If you want even more examples using the tower power rule we mentioned, you can go look at section 4.4 on graphing with asymptotes. All right, so that's this portion of our final exam review, and I believe the next one I am going to tackle optimization problems, which is section 4.6. All right, now if you haven't finished the homework on optimization yet, then I strongly suggest watching the next video on optimization. It has a few more problems that I think will be helpful for you when you do that homework. All right, well then I'll see you next time where we will have more fun with math.